Okay, here we go with the surface hardening right quick. Talk to you about a little bit about the surface hardening. It's a very selective heat treating process, but nonetheless, it is a hardening process, and sometimes referred to as case hardening because you're just hardening the outside edge, outside thickness of these components. And I've got a nice little spiral or a bevel gear here to show you. And this is an excellent example because on these, what they'll do is they'll use a plain carbon steel for its toughness properties, and yet they'll then diffuse through the surface hardening carburizing method, diffuse carbon into the surface of these tooth profiles, and then so they get the net result is they get a very hardened tooth profile surface, but yet a very sort of a tough inner core, kind of like an M&M kind of a thing, you know. So that's what's accomplished and very practical and very much used in all types of gear applications. So I thought I'd bring that and show that to you. Uh, but anyway, these surface hardening or case hardening processes are technically a diffusion treatment. Okay, a diffusion treatment, going back again to fixed law on diffusion. And again, it is a carburizing process because diffusing carbon into the surface of a mechanical component like a gear. So we're actually diffusing it into there. And if you recall, this is a little handout here about that. And of course, you can diffuse things interstitially speaking, which is what we're going to be doing with carbon into iron, or it can also be done substitutionally. But basically, it's going from a solute into a host atom here, and then the solute atoms go into the host atom here. But one is interstitial, which is what we're going to be talking about with respect to carbon and iron. So that's the basics back on diffusion. Um, so, but the two methods to do this. There's a sort of called a solid method, which uses solid particles of highly carbonaceous type material, carbon-based material, which usually is in the form of charcoal or coke or coal or something like that. And those are small particles basically, and they are packed around a component like this gear. Now, the only thing that's lacking is because it is diffusion, is a thermally activated process. So we have to add a certain amount of heat to this whole process. And I've got a little schematic of a pack carburizing treatment here. And so you see there's this large container, a sealed steel container here, and then this is the part here, and it could very much be this, almost fits in there. But be that as it may, this is the part, and it's surrounded by all this. They're using just activated charcoal all around this whole part, and the lid's put on, and then they subject it to whatever temperature it needs for this particular alloy, the steel. And so there's two things a factor here. There's time and temperature. So you need to have it at the right temperature. You need to put it in for the right time, because the longer you leave it in there, the thickness of this diffusion, as you know from that flux equation, that thickness will continue to grow as this diffuse, these solute items diffuse into the thickness. So it's very critical that you not only get the right temperature, but you put it for the right time. All right, so you get the exact thickness that you're looking for. All right, so this is a good example of what a pack carburizing process might look like. Okay, and then the other way you can do that, you can go through a gas processing, and usually these are called nitriding or carbonitriding, and simply kind of similar, but instead of infusing carbon around it, you're pumping it full of gas, and a lot of times they use ammonia, which is NH3. And they don't have to heat it quite as much at all, but it really does impart a very hardenable surface at that on the surface of those components. Now, let me mention something to you. This does not harden the surface. This is just a diffusion process. In other words, all we're doing is we're giving it the opportunity to be hardened. Just by putting this in and going through this carburization process, this pack solid particles thing. Just doing that doesn't make this surface that much harder. But what it does is it gives it the opportunity, which we'll see here in a moment on the IT diagram, allow it to be hardened. Otherwise, there wouldn't be enough carbon in here to harden it. So there's the key, and that's why they do this. Okay, so they can have a chance to put it through a hardening process. And to do that, again, we're going to use two different methods to impart that temperature on this particular one. And as I said before, you can either do a flame hardening, what they call a flame hardening, or an induction hardening. So flame hardening, to get this up to temperature, you would bring it up with a flame. Otherwise, you can do it through an induction, through electrical transformation. Okay. All right. So let's look at now. This is strictly the heat treating side of this. This is not the carburizing side. This is the heat treating side of this. Once you have the fused carbon into these teeth profiles, then you do go through either a flame or induction to heat the outside edges of this thing and then quench it. And again, you can get the temperature, the heat provided by either a flame, oxyacetylene, or through electrical induction current. Does the same thing, and then once it's heated, goes right back to the second step, which is quenching, and you're done. Okay, so that's what that's about. Now, just briefly on these softening processes, if you recall back from your material science, there are softening processes. Basically, when we try to take a part that has been cold worked or overly cold worked, you bring it back to its pre-cold work conditions without sacrificing any of its geometrical forming changes that have taken place. But you're just bringing it back so it's not quite as brittle and will regain some of its inherent toughness properties. And so we go through a series of annealing processes. There are a lot of different types of annealing processes, but they're all kind of lumped together. But there's three stages. There's a recovery stage, a recrystallization stage, and then a grain growth stage if you allow it to persist, allow it to go on. But again, all that's doing, these annealing processes are just softening, and they're just usually trying to bring back a component to its pre-cold work conditions, and it's not so hard and not so brittle. Then finally, there's a tempering softening process, which is used primarily when the formation of martensite occurs. It is again kind of doing a compromise. When you temper something, you're bringing it back down from a very, very hardened state to a more relatively usable, tougher state, but still have some of the qualities of the hardness and the strength still there. So at any rate, this is basically the three types of heat treating processes: two hardening and one softening process. So now what I want to do is talk to you about the IT diagram. So let me erase all this right quick. All right. Okay, so now we're going to look into this, and basically what we're looking at here is something called the time, temperature, transformation diagram. Actually, diagrams, okay? Also referred to also as the ISO, and this would be, of course, the TTT diagram, and this would be the isothermal transformation diagram. Okay, and in the past, the diagrams, especially the phase diagrams, there was no factor with respect to time in any of those phase diagrams, because we always said it was just subject to what we call equilibrium cooling, which means it just basically allowed to cool on its own accord from a liquid all the way down to room temperature. Where this is completely changed, because now we're invoking this factor. Time is now going to be a factor in these diagrams. So in other words, we're going to force the cooling of these metals now, these different alloys. And as a result, we're going to gain what's called a isothermal transformation curve, or a time temperature transformation curve. Now, this is what this looks like, and I'm going to look and see just how big that is. I'm going to try to make that a little bit larger if I can. Here it is. All right. So, as long as I keep it there, I know where it is. Right there, right there, right here, right here. Okay. So this is what a isothermal transformation diagram looks like. It's a typical diagram, and one thing you have to remember is that these diagrams are specifically for one particular alloy. Okay, it's for one particular alloy, and so it really doesn't matter. But I think we should probably just call this maybe a since it's using this 1333, which we know that's the lower transformation temperature, and it's using that for its austenitic temperature, I think we should go ahead and call this a number 1080, which would be a plain carbon steel with 0.8% carbon. So that's kind of what this looks like. All right, but again, every steel alloy will have its own time temperature transformation, or IT diagram or curve, okay, because it helps us determine what particular product we were going to get out of this. Now there's three possible products out of this, and one of them is called pearlite, which you already know a little bit about. The other one is called bainite, and the other one is called martensite. So we'll go through those to tell you about what this is. So essentially, there's kind of a dividing line, and it usually shows up right around the nose of this curve here. And so everything above this would be a pearlitic product. Everything below this would be a bainite product until you get down to here. And this is the dividing line between bainite and martensite, this line right here. All right, so what we have here is a steel, and it has been heated up, austenitized up here, so the curves will always start here. So what we're trying to do is generate cooling rate curves. All right, cooling rate curves. That's what we're trying to generate here, or cooling rate curves. Cooling rate curves. All right, and it's all based upon quenching methods. Quench methods. Because here is our time factor right here, and it's a logarithmic scale of time, and so depending on whether you quench it aggressively with brine or water or oil, you're going to get a different trajectory. You're going to get a different cooling rate curve, you see. Now, this is a very particular specific curve, because when you have a curve that gets really, really close, and this is like a nose right here, kind of, if you look at it, nose of the curve. If you get real close to this nose but don't touch it, this is called the CCR, which stands for the critical cooling rate curve. All right, the critical cooling rate curve would be something like this. Now, let me talk to you about these products. All right, let me talk to you about these products. Now, there is a start, there's a finish line. The start line, I'm going to draw in green, of course. So this is the start line of this whole curve. All right. And then this is the finish line in red. Okay? So, what that means is that anytime this cooling rate curve goes through this, and there's the timer, anytime this cooling rate goes through this part, a starting line, you're going to get this particular product. And so we said here, this is all perlite right here. I'm just going to draw it like this. And this is the only really region we're looking at. This is the perlite. Down here, below this line, and through here, this is going to be all bainite in here. All right. And this is, of course, all perlite inside here. So if you have, let's just say, simplistically saying, let's just say we had a cooling rate curve that looks like this. It starts up here, and then it's, let's say it's oil. It's not very aggressive. And so the cooling rate curve basically kind of goes like this. All right. So what that tells you is that it entered right here, all right, within 10 seconds it had started from austenite, unstable austenite. It started turning to perlite right here after about 10 seconds, you see. And then it kept going nonstop without anything changing, kept going, and then it finished right here in about, looked like it took maybe, I don't know, 20 seconds or so, because again, this is logarithmic. So maybe it took 20 seconds to completely finish. So what the product you would have gotten out of this quench from this particular steel would have been a 100% perlite structure. And you know what that looks like, okay? You remember what that looks like. It's just a bunch of all those plates, all right? A 100% perlite structure. All right? So if we did not do that, if we looked at something that if we did the other extreme would be something that looked like this. Let me use a different color here. Well, I'll just use black. Here it is. Okay, so if we did the other extreme and we chilled it with, let's say, brine, notice that this curve never got into the start, or never got into the inside of this area here. Never touched there. So it bypassed all that because it was a very aggressive quench. And in probably less than, if you look at here, come down here, probably less than 8 seconds or so, this thing went from 100% austenite to 100%, now we have 100% martensite. A 100% martensite, because it never went inside here. All right. So there's lots of different, and I'm not going to get into the details of this because it's too long and lengthy, and this is not a material science class technically, but there are lots of different curves that can be, cooling rate curves that can be generated. And so you can get a multiple of products. You could get a product that is, let's say you could get 50% perlite plus 50% bainite. You could easily get a product like that depending upon how this curve goes. Now this curve would have to start in here and then finish out here. So you'd have to do some weird things with respect to how that cooling rate curve goes, but there are ways to do that. And again, I don't need to give you all the details how that's done. But you can go in here and get about 50% perlite and then quench it slower, and then a little more time here, instead of going completely down like this, and come out with a bainite product. So you'd have 50% perlite, 50% bainite. You could also get something like a 50%, another possibility to get a 50% perlite and 50% martensite. Okay, by coming in here and then just continuing down, and you got about 50% here, and it never goes out here. So this goes through a starting line, not a finishing line, so it bypasses this and goes into martensite. So whatever the maximum percentage you got here would be the leftover. The conservation of mass would be the leftover, and call that martensite. Okay, so this is just the basics of what these cooling rate curves for. And again, what you need to remember is that every alloy will have its own particular cooling rate curve. And this gives the heat treaters and the metallurgists an idea of what the possibility of these products are. All right, what the possibility of these products are. And to show you what that is, kind of summarize that right quick. I've got another table here to show you what that looks like. So if we look at that, all right, let me make that a little bit. There we go. So this shows possible transformations from one of those diagrams. First started austenite. If we do a slow cool, I showed you how we could get pearlite. We did a moderate cool, we could get bainite. If we get a really rapid quench, a very aggressive quench, usually with brine or something, we'd come up with martensite. Okay, and from this is the general trends for the properties. All right, martensite is obviously the hardest part, the hardest potential. Perlite, other than spherodite, we're not going to worry about that. Would be the softest. So look at this as. Here's the top product, martensite, and then tempered martensite, bainite, fine perlite, coarse perlite. Okay, so obviously from here going this way, the strength increases. From here going this way, the ductility, all right, increases. All right, so you have maximum ductility down here with this coarse perlite as opposed to martensite. Okay. And these are the options you have when looking at these isothermal transformation diagrams. Being able to get one of these three products, and as a result, you'll have specific properties. Now, one of those properties you'll get out of this are both hardness and strength. Okay? Not very hard, not that much strength. A harder product with a little bit more strength, a very hard product, and ultimate strength. But this is too hard to use, so that's why you have this another box here called tempered martensite. So all we're doing is we're reheating it, we're kind of softening it up, but we're we're putting back in place some of the more qualities of toughness, ductility back into this, but still maintaining a lot of that strength achieved from this martensite. Now again, this martensite is a completely different phase. It's not an FCC. It's not a BCC. It's a diffusionless transformation. All right, diffusionless. So it takes place very, very rapidly, and it forms a body-centered tetragonal. All right. So there's a summary of the possible transformations. I want to talk to you a little bit about hardenability, and I will a little bit later. So we'll have to do one more slide or video on this, and we'll wrap this part of it up. So we'll talk to you soon.